So what I have here is this should be equal to the P alpha, the X delta, Q subscript alpha, plus P alpha, the Q alpha, the X over here, delta. Now plus what I've got here is gamma alpha, N delta, Pn, and over there is Q alpha, minus gamma here, N alpha delta, P alpha, and over here I believe is Qn. Qn. Okay. Now looking at this, you can see that I can perform one of our very popular transformations, which will be interchanging N and alpha here in this last expression. N and alpha. Why do I want to do that? Because I have a feeling that this will look rather the same with what I already have here for this term. You can see that if alpha here is replaced with N, and N here is replaced with alpha, and the same happens for this, then I have these two last terms to be the same. For instance, I'm going to have straightforward. This, of course, I'm not touching. So everything there is the same. But here, I'm saying that my N becomes an alpha, the alpha becomes an N, delta remains what it is. The alpha here becomes an N, and the N here becomes an alpha. So we can see that these last two terms cancel because they're just the same except for the signs. So what I'm left with is that, which, by the way, when you look at very carefully, is the same as saying d dx delta of P alpha Q alpha. That's what those first two terms look like. Right? By the initial Leibniz rule, expanding this, you obtain that. So what do I do next? What I do next is simply to look at the fact that the covariant derivative of a scalar, which we set out to prove, we chose for our scalar some dot product between two vectors, which is that and that. We took the covariant derivative, and finally what we obtained was simply the partial derivative of this. So this is with respect to x delta. So P alpha, Q alpha, x delta. Well, but by the way, what was this right from the beginning? This was phi, comma delta. So we have indeed shown that this, sorry, I think I need to be careful with writing this to make this very apparent. We have shown that phi delta is equal to this. That is what we have. And it's an expression we have been using quite very often, every now and then. So next, we want to show the four-dimensional D'Alembert. That's what we'll make. Well, it's still the same D'Alembert, but what we call it now is the covariant D'Alembert. Covariant D'Alembert in the sense here that what we have here are two expressions. So let me give you a feel of what this will mean. Okay, this will mean, for instance, so the usual D'Alembert, maybe this, that is what you have. But instead of partial derivatives, you have covariant derivatives replacing this. And this is what we have written over here. So we want to show that this expression is equal to that. Okay, very quickly, so we proceed as follows. We take this to mean phi delta here, and then here outside we have something like that. So how do we proceed? We proceed by noting that we can rewrite what is inside as G gamma delta phi. Of course, what we have done is to have lowered this, change it to gamma, and that is what we have. Of course, this now looks like what we already know, or how to handle. At this point in time, what we simply have to do is to define the covariant derivative of this. But maybe for a start, we want to start from dealing with the outside first. We can call this whole thing some T gamma delta gamma. So that this is the same thing as T gamma delta gamma and that. Exactly. So that this is what we get. In other words, we are going to find the covariant derivative of this object. Play with it for a while before we substitute what we know it to be actually. So, first of all, you have that T. Oh, let me just go to the other side quite straightforward. T gamma delta gamma, covariant derivative with respect to this. So the usual thing, gamma delta gamma, I differentiate with respect to x delta. I want to contract the first two indices on the top. So I'm going to use some n here, and T here will be replacing n. I'm contracting gamma. Delta stays as it is, and the gamma here remains. I'm differentiating with respect to that. Plus, I do the same thing again. I want to contract, let me say, of course, the next thing should be delta. This is gamma. Delta here becomes n. And I'm contracting delta, so delta moves over. I'm differentiating with respect to delta, and this is what I get. And the gamma that was there becomes left alone. So next, minus gamma, because I'm contracting the lower index, which is gamma still, with some n here. And so what I'm contracting is gamma, it moves over down, and the delta here stays here as usual. Then the upper indices remain untouched, gamma delta. This is what I get. Oh, yeah. Everything looks fine. Now, of course, looking at this expression, we can tell already from the last two, I guess, yes, no, not the last two, these two terms. We just need to make one of our very friendly or old friend transformations, and then we can find something similar. On this term, for instance, if I make the transformations between, I'm guessing, gamma and n, right? Gamma and n, you can see that the two expressions remain are the same except for the signs. Yeah. For if I replace n here, so if I replace n here, the gamma here with n, I have something like this. And of course, my n here becomes gamma, and the n here also becomes gamma, and that's what you have. Of course, I have a gamma here also which changes to n, and that is what you get. So straightforward, without wasting so much time, those two terms cancel. And what I'm left with is this, gamma delta, gamma, the x delta, plus what I'm left with here is that delta t gamma n gamma. Again, at this point in time, looking at this particular factor, yes, this is something we have been very used to. But in order to help me see how I can combine it with this first term, I'm going to perform a transformation also on this factor. Sorry, the whole term actually, not just the factor, but it's because it will help me on that factor. And that's interchanging n and delta. Now, if I were to do that, I could do that because n and delta are dummy indices. So I have this gamma delta, gamma, now the x delta. So this will be plus gamma, this becomes n, and this is delta, and this is n. And this gives me t. The gammas remain what they should be, the n alone changes to delta, and this is gamma. Why did I do this? Because then it means that this affine connector becomes this. Now, if you remember, I think we've used this over and over again. This is not the dummy index, so that is why this becomes it, delta minus g. Of course, at this point in time, you can see that I have the x delta here and the x delta. And somehow, quite magically, should I say, the t gamma delta gamma here is just the same as that. So you can see that when I make this substitution, t gamma delta gamma delta is equal to the t gamma delta gamma, the x delta, plus 1 all over the square root of minus g, d the x delta, square root of minus g, t gamma delta gamma. And the two, of course, as usual, can be combined as this, minus g, d the x delta, and the product of minus g, t gamma delta gamma. And that is it. This, at this point, this is as far as we go. Of course, we can see this is exactly what we usually get. So, very quickly, moving on to go on with what we expect to find. So, we have just shown straight out from the beginning that this expression for the covariant derivative of that is equal to 1 all over the square root of minus g d dx delta square root of minus g t gamma delta gamma, and that's what we get for that. Okay, now looking at this, what do we do next? Well, we just have to remember what t was. T gamma delta gamma, we said originally, was equal to g gamma delta phi gamma. We have of course shown that this is the same thing as this is gamma delta. We said this is the same thing as just comma gamma, right? It's one of the proof we just finished with before proceeding with this. Now, what do we do next? What we do next is simply substitute that back into the original expression, which we have rewritten. This is a delta. We said that this was supposed to be equal to here, g gamma delta phi here, that, and then that. Of course, here what we have done, we have shown what we have here to be in the middle, whatever is inside here to be in the case our t. And so what we can do is simply just go straight into saying that this is the same thing as t gamma delta gamma, that, and we have already obtained this to be that expression over there. So what we obtained was 1 all over, so first of all, this is our t entirely. Yeah, exactly. So looking at this expression, we simply go ahead and say this is 1 all over the square root of minus g d dx delta, looking just very much like what we had originally, d dx delta okay. Okay, so of course, as we can see, everything just cleans out so perfectly. As we can see over here, what we decided to show was this expression here, which gives us that. Now in the end, we can see that this is already equal to that, like we've already shown. And this being equal to that, the d dx delta here, we just represent with a comma over here. And the t gamma delta gamma, which was what we named this in the brackets, we can see was already initially equal to this. And we already stated and have shown in our last proof that this is equal to that. And so because of that, we can simply just substitute back into that expression. So in place of this, we simply put that. And so we can see that we have shown the expression already, that the covariant D'Alembert, which we have already wanted to set out, we set out to show right from the beginning, is equal to that. So this is a very wonderful expression, and it's something we can apply in any kind of manipulation that involves the covariant derivative, the D'Alembert of any scalar. So